All right. One of the things we usually care about is the pressure drop in a duct like this, right? You're unlike in external flow where, let's say, it's the wind blowing something over your plate, or you're driving your car and you have flow going over the car, but you don't really care too much about the pressure drop, at least for the convection correlations or whatever you're doing. Unlike that situation in internal flow, it's almost always the case that somebody is paying to move fluid through that system. Or you have a pump, you have a fan, there's gravity head or whatever it is that's driving that flow through that duct or pipe. And so we actually care a lot more about the pressure loss, or the reduction in pressure across the pipe, than we do in external flow. So we want to come up with an understanding of how the pressure loss relates to some of the forces in that we've been talking about here. So let's draw our duct again. Draw a rectangle. Okay. So we have our duct, and what we want to do is let's actually do an X momentum energy, or an X momentum balance. So let's look at here this control volume in the duct. And we're going to draw the control volume from the top of the duct down to the bottom of the duct, basically the entire cross-sectional area of the duct. As opposed to drawing it like what we've been doing for boundary layers, we have both a dx and a dy component. Here we're drawing this for the entire vertical, or the entire area at some position x. And so why can we, here's x and here's x and here's y. So why can we do that, or why would we do that? Well, because if we're just concerned with the x momentum part of it, we can just draw the forces that are acting on this control volume. And we, let's say, so for example, we have, what are the forces acting on this? We have a shear stress. Right? So if flow is going to the right, we're going to have a shear stress pushing back on this control volume. So if I just call this shear stress tau s, and actually the full shear stress is tau s times the perimeter of the duct times dx, that gives me the force without even needing to go into the detail of doing a control volume on dx and dy, right? I'm just calling the effects of the y velocity gradient tau s, and I'm kind of punting it to that model. So if I do that, then I can just do the control volume in its entirety this way. Okay, so this is a x momentum. So let's write out actually here, this would be, what are we trying to do? We're trying to take the sum of the forces in x plus x momentum in is equal to x momentum out plus any change with respect to time in x momentum. Okay, this is, let's do this for a steady problem. So it's not changing with time, so that goes away. And we do need to consider both forces in x and momentum in and momentum out. So what are the forces we have in x? So we have that tau that I already drew. That's certainly going to be a force in the x direction. We also potentially have pressure. So you might have pressure acting on this control volume. So that pressure would be, let's see, over here it would be P times the cross-sectional area AC at position x. Over here, it's going to be P times AC at x plus dx. Okay, we also have, so that's our forces. I don't think there's any other forces. We have x momentum in and we have x momentum out. So the momentum in is going to be what? It's going to be the mass flow. So that's going to be rho times u. It's going to be the mass flow times the velocity. So that's also u. It becomes rho u squared. And then we're taking the integral of this, because you have a velocity profile, u, that's a function of y, or a function of position in the duct. We have to take the integral of this over all area. So we'll do the area integral a over AC of this quantity dAc. Right? And this is going to be all of this at position x. And then we have leaving the same thing, but at x plus dx. So AC rho u squared dAc at x plus dx. Okay, so that's our force balance, or our momentum balance on flow in the x direction in this duct. And again, the point is we want to come up with an understanding of pressure drop. So let's take this and write it out in an actual expression. So we have here rho AC at x minus tau s times parameter times dx minus what's leaving pressure-wise P AC at x plus dx. So why did first of all, the pressure, we have pressure to the right in the positive x direction, and we have pressure to the left in the negative x direction. So that's where you get the signs. Sorry, it's not P. I did that last time. P, pressure times cross-sectional area at x minus pressure times cross-sectional area at x plus dx. Okay, so that is the pressure plus the shear, noting that we drew the shear stress to the negative x. Okay, and then we have to add to that the momentum part of it. So this is integral of AC of, let's see, rho u squared dAc at x. And then that's equal to, on the right-hand side is just the area integral of rho u squared dAc at x plus dx. Okay, so that's just writing out the balance there. Okay, so we go through and we'll do the same expansion. I don't know if I need to write out the expansion, but you end up canceling out everything except for the differential term. The pressure goes away except for the differential part of it. So here we end up with, if we kind of rewrite this, we end up with, let's see, minus the differential of P AC dx is equal to tau s times the parameter plus d dx of the integral, area integral of rho u squared dAc. Let's see. Yeah. Sorry, I ran out of room there, but that's evaluated at x. Okay, so sorry, that's a little messy. It's tau s parameter plus the differential of the area integral of the momentum term evaluated at x. So then we can rewrite this. This ends up being the following. So it ends up being minus dP dx, right? We're trying to get this pressure is equal to tau s times parameter over AC plus d dx of 1 over AC integral of AC rho u squared dAc at we already evaluated it there. Okay, so it's a little sloppy. Let me move this over so you guys can see it. Okay. So d dx of, yeah, so the d dx goes around this term. Okay, that's the thing we need to look at here. Sorry for the sloppiness. But what we see here is now maybe something interesting. We're seeing my pressure gradient, the loss of pressure, dP dx, that pressure gradient is negative. So it's negative with what? Positive shear stress. And it's negative with a change, an x change in momentum. Right? It's negative with shear stress and x change in momentum. So now we can think about, okay, where are these different terms actually important? So let's look down here. Let's see how to do this. So I'm just going to copy this down here rather than rewrite it. Hopefully. So let's see. So we have this as our expression. Okay, so what we're seeing here is now where there's kind of two regions where we can look at this equation. There's a developing region where there is a change in momentum in the developing region. Once it's fully developed, it's no longer a change, and it's just only the shear stress term. So let's actually take this and plot out let's plot the pressure P as a function of position X, and let's say that at this location here, flow becomes fully developed. So this is XFDH. So at that position. So let's start first of all looking at in the fully developed region. So in the fully developed region, if we look up here at this velocity profile, my velocity profile is not changing as a function of position. So d dx of an area integral of a change of a velocity, right, is going to be 0. There is no change in the momentum as a function of x in the fully developed region. So in that region, this term goes away. That doesn't mean then that my pressure is constant. There's still a shear stress effect, but my pressure in that region is going to be related to a perimeter over cross-sectional area that's constant times the shear stress tau s. And in the fully developed region, that shear stress is going to be constant. Okay, so if I plotted my pressure in that region, it's going to look something like this, right? It's a constant, linear profile. So I'm still losing pressure. The further I go on x, I'm losing pressure, but it's a constant loss of pressure. Okay, if we go then to the developing region, now we still have tau s. We still have shear stress, and actually that shear stress gets quite a bit bigger because now my delta t here, or delta m, is getting smaller, so my shear stress is getting bigger. There's a bigger gradient, velocity gradient. So we're going to see an increase in shear stress as a function of position, but we're also seeing that the momentum of this is changing. We're going from constant velocity to, in the inner core of this, an increase in velocity. And because we have u squared here, an increase in velocity is going to count for more momentum than a corresponding decrease in velocity, right? Because it's a u squared quantity. So over here we see my pressure loss is a function of position in the developing region. It's going to look something like this, right? Where over here we have a really steep gradient, and over here we have a much less steep gradient, just because of those effects. So we have two things going on in developing region. We're accelerating the flow in the core. That leads to an increase in momentum. And so over dx region, you see that showing up in additional pressure loss. And we have an increase in shear stress because of the smaller boundary layer.